This question is to do with thermodynamics, and in the first part we are asked to define the term enthalpy of lattice formation. When we break this down, we have the term enthalpy, which relates to energy, the term lattice, meaning 3D arrangement of atoms or ions in a structure, and the term formation, meaning the production of something, which in this case is 1 mole of a solid ionic compound. So using these 3 key bits of information, if we put all of this together, our definition is the enthalpy change when 1 mole of a solid ionic compound is produced from its gaseous ions. So in the next part of the question, we are given some enthalpy change data in table 1. We are told that the enthalpy change of solution for AgI is 112, and the enthalpy change of hydration for Ag plus and I minus are minus 464 and minus 293. So if we draw this out, we have AgI in the solid state going to Ag plus in the aqueous state and I minus in the aqueous state across the top. Now, as we are asked to calculate the enthalpy of lattice formation of silver iodide, we will draw the second arrow of the cycle up, with the third arrow going up to the ions in the aqueous state. If we now input some values, we have 112 across the top, and minus 464 plus minus 293. So if we put that into our calculator, we get minus 757, and that is on the third arrow. Now, as we don't know the value for the enthalpy of lattice formation of silver iodide, we will call this value x, and now we can begin to solve. So as we are going against the arrow, our x becomes negative, and this is always the case whenever you go against an arrow. So we have minus x plus minus 757, and that is equal to the total of 112. Now, if we rearrange the equation by moving x to the right and the 112 to the left, we get x equals minus 757 minus 112, which if we put into our calculator, we will get minus 869 kilojoules per mole. For this question, we are told that a calculation of the enthalpy of lattice formation of silver iodide based on a perfect ionic model gives a smaller numerical value than the value calculated in part 2. And we are told to explain this difference. Now, immediately from the compound silver iodide, we can tell that this is a covalent compound, and this is because we have a metal and a non-metal bonding together. The reason for the difference is because of the perfect ionic model, assuming that there is only electrostatic forces of attraction between the oppositely charged ions. So as there is a difference in values, which is stated in the question, silver iodide must have some covalent character and mustn't be purely ionic. And for the second mark, as our actual value is larger than what is stated by the perfect ionic model, the forces within the lattice must be stronger. And now for the final part of the question, which asks us to identify a reagent that could be used to indicate the presence of iodide ions in an aqueous solution, and then to describe the observation that's made. So this is part of a required practical, where you will have some test tubes and have to add a reagent to each of them. Now, the most common answer will be adding silver nitrate, which has the chemical formula AgNO3, and this will result in a yellow precipitate being produced if iodide ions are present. This question is about acidic solutions, and in the first part we are told about the acid dissociation constant, also known as Ka, and its value of 1.74 times 10 to the minus 5 for ethanoic acid at 25 degrees Celsius. We are then told that a buffer solution with a pH of 3.87 was prepared using ethanoic acid and sodium ethanoate. And in this buffer, the concentration of the ethanoate ions was 0.136 moles per decimeter cubed. We are asked for 3 marks to calculate the concentration of ethanoic acid in the buffer and to give our answer to 3 significant figures. Now the first thing we are going to do is put in the values that we know into the Ka equation that's given. So that is the value for Ka and the concentration of the ethanoate ions. We can work out the H plus concentration by using the equation pH equals minus log H plus, where we inverse the equation to find the H plus concentration by doing 10 to the power of minus 3.87, which gives us a value of 1.3489 times 10 to the minus 4. It is important to store this value on your calculator to ensure that you get the correct answer in the end. We then need to rearrange the equation by dividing by our Ka value and multiplying by our unknown value of ethanoic acid concentration. And when we put this into our calculator, we get an answer to 3 significant figures of 1.05. This next question is a 6 marker and tells us that in a different buffer solution, the concentration of ethanoic acid was 0.26 molar and the concentration of ethanoate ions was 0.121 molar. We are then told that a 7.00 times 10 to the minus 3 mole sample of sodium hydroxide was added to 500 centimeters cubed of this buffer solution. We are then asked to calculate the pH of the buffer solution after the sodium hydroxide was added. Now we will begin by writing out the Ka equation, which is the concentration of CH3COO-, the concentration of H+, and then divided by the concentration of CH3COOH. For this type of question, I always separate my page to distinguish between the acid and the base. So if we work out the moles of ethanoic acid by using the equation of moles equals concentration times volume, we will do 0.26 times 500 divided by 1000, as concentrations are needed to be in decimeters cubed rather than centimeters cubed, and this will give us a value of 0.13. If we now do the same for the moles of the ethanoate ions, we will use the same equation and do 0.121 times 500 divided by 1000 to get an answer of 0.0605. Now a 7.00 times 10 to the minus 3 mole sample of sodium hydroxide was added to the 500 centimeter cubed sample of the buffer. So this means that we will have to subtract this value from moles of acid, but add it to our moles of the ethanoate ions, as the definition for a buffer is a solution that resists the changes in pH when a small amount of acid or alkali are added. Therefore, we will do 0.13 minus 0.007 to get 0.123, and 0.0605 plus 0.007 to get 0.0675. Now, although the equation states using concentrations, as we are dividing through by the same value for both, the ratio is always going to be the same for our acid and salt. So we can just keep this in moles. Now, as we want pH, we need to rearrange for H+, and then input our values. So we will do 1.74 times 10 to the minus 5 times 0.123, and then divided by 0.0675, which gives us a value of 3.17 times 10 to the minus 5. And if we use the pH equation of pH equals minus log of H+, we get an answer of 4.49. So our final answer to 2 decimal places is 4.50. Now, if we look at where the marks are allocated, we get a mark for working out the moles of ethanoic acid, a mark for the moles of sodium ethanoate, for the moles of CH3COOH after addition, so that is the value of 0.123, and also the value of 0.067. We then get a mark for working out the H plus concentration of 3.171 times 10 to the minus 5, and then putting that into our final equation to get an answer of 4.50. This next question is to do with the ionic product of water, which is stated as a value of 2.93 times 10 to the minus 15 at 10 degrees Celsius. Now, water dissociates into hydroxonium ions and hydroxide ions, so an equilibrium exists, which is H2O plus H2O goes to H3O plus OH minus. Now, if we remove one H2O from both sides, this simplifies to H2O goes to H plus OH minus, and if we apply our knowledge of equilibrium law using Kc, we will get Kc equals the concentration of H plus multiplied by the concentration of OH minus and then divided by the concentration of H2O. As water only dissociates by a small amount, the equilibrium lies over to the left. Thus, the concentration of H2O is so large compared to the concentration of H plus and OH minus that is taken as a constant. If we now multiply our first constant Kc by the concentration of H2O, which is now also another constant, we get a new constant with the symbol Kw, which equals the concentration of H plus multiplied by the concentration of OH minus, and this gives us an answer of C. The next part of the question asks us to calculate the pH of pure water at 10 degrees Celsius and to give our answer to 2 decimal places. Now, in pure water, there is always one H plus ion for each OH minus ion. So the concentration of H plus equals the concentration of OH minus, which means that we can write Kw as Kw equals the concentration of H plus squared. So if we sub in values, we will have 2.93 times 10 to the minus 15 equals the concentration of H plus squared. And if we square root both sides, we will get a value for H plus, which gives us 5.413 times 10 to the minus 8. And then if we use the pH equation of pH equals minus log of H plus, we should get an answer to 2 decimal places of 7.27. Now, for this next question, we are asked to suggest why the pure water is not alkaline. And we know that when water dissociates, it produces, in a simplified form, H plus and OH minus ions. Now, we actually used this in the last part of the question, but the answer is because in pure water, there is always one H plus ion for every OH minus ion. So, therefore, we know that the concentration of H plus equals the concentration of OH minus. In this question, we are asked to calculate the pH of a 0.0131 molar solution of calcium hydroxide at 10 degrees Celsius for 3 marks, and to give our answer to 2 decimal places. Now, calcium hydroxide is dibasic, which means that the OH minus concentration is twice the concentration of the alkali. So we need to multiply 0.0131 by 2, and we should get a value of 0.0262. So if you write out the Kw equation now, we get Kw equals the concentration of H plus multiplied by the concentration of OH minus, and if we sub in values, we will get 2.93 times 10 to the minus 15 equals the concentration of H plus multiplied by 0.0262. So if we divide by 0.0262, we will get a value for H plus of 1.118 times 10 to the minus 13. And then if we use the pH equation by subbing in our value for H plus, we will get an answer of 12.95 to 2 decimal places. For the final part of the question, we were told that the calcium hydroxide solution was saturated and that a student added 0.0131 moles of magnesium hydroxide to a 1 decimeter cubed volume of water and stirred the mixture until no more solid dissolved. We are then asked to predict whether the pH of magnesium hydroxide is larger, smaller, or the same as calcium hydroxide. So this question tests your understanding of solubility down group 2, and we know that as you go down group 2, the solubility of hydroxides increases. So using this fact, we know that the pH must therefore be smaller and more acidic. In this next question, we are told about a sample of titanium that was ionized by electron impact in a time-of-flight mass spectrometer. And that information from the mass spectrum about the isotopes of titanium in the sample is shown in Table 2. We are then asked to calculate the relative atomic mass of titanium in this sample for 2 marks, giving your answer to 1 decimal place. So, firstly, in these types of questions, I would always check that our abundance adds up to 100. And if we do 9.1 plus 7.8 plus 74.6 plus 8.5, we do get 100. Now, the relative atomic mass is defined as the average mass of an atom of an element on a scale where the carbon-12 isotope is 12. So using this definition, we can now solve by summing each of the mz values, which is the mass to charge ratio, multiplied by the abundance, and then dividing by the total abundance, which we've already worked out as 100. So if we do 46 times 9.1 plus 47 times 7.8 plus 48 times 74.6 plus 49 times 8.5, and then all of that divided by 100, we should get a value to 1 decimal place of 47.8. The next part of the question asks us to write an equation, including state symbols, to show how an atom of titanium is ionized by electron impact, and to give the m/z value of the ion that would reach the detector first. So this examines our understanding of what electron impact is, and we know that it is a type of ionization where a high energy electron gun is used to fire electrons and form a positive ion. So we can write this as Ti goes to Ti plus E minus. Now, another important factor is that the sample is vaporized first. So we can add gas state symbols in, and this gets us the mark. In terms of what reaches the detector first, we know that during the acceleration phase, the ions are accelerated to have the same kinetic energy. So because of this, the answer must be the lightest ion, which in this case is 46. The third part of this question asks us to calculate the mass in kilograms of 1 atom of titanium-49. And we know that using the periodic table, 1 mole is equivalent to the relative atomic mass. So for titanium, 1 mole is equal to 47.9 grams, but in this question, 1 mole is equivalent to 49 grams. And if we divide this by 1,000, we will get our answer in kilograms of 0.049 kilograms. Now, if we use the Avogadro's constant with a value of 6.022 times 10 to the 23, and divide this by our value, we will get the mass of 1 atom, as the Avogadro's constant tells us the number of atoms in a mole, and thus this will give us a value of 8.137 times 10 to the minus 26. For the final part of the question, we are told that in a time-of-flight mass spectrometer, the time-of-flight T of an ion is shown by the equation, which actually combines 2 well-known equations of E equals a half mv squared and V equals distance over time. We are then told that in this spectrometer, the kinetic energy of an ion in the flight tube is 1.013 times 10 to the minus 13 joules. and the time of flight of a titanium-49 plus ion is 9.816 times 10 to the minus 7 seconds. We are then asked to calculate the time of flight for the titanium-47 plus ion and to give our answer to an appropriate number of significant figures. Now, if we sub in values that we know, we can work out the value for distance of the flight tube. So we should get 9.816 times 10 to the minus 7 equals distance multiplied by the square root of 0.049 in brackets divided by our Avogadro's constant value of 6.022 times 10 to the 23, then divided by 2.026 times 10 to the minus 30. And if you rearrange this to get d by itself by dividing by our whole square root, we get a value of 1.55 to 2 decimal places. So now we can work out the time of flight for the 47 plus ion by subbing in our new value for distance, which we should have saved fully on our calculator. So doing this, we get our value of 1.5489 multiplied by the square root of 0.047 in brackets divided by 6.022 times 10 to the 23, then divided by 2.026 times 10 to the minus 13, which gives us an answer to an appropriate number of significant figures, that is 9.61 times 10 to the minus 7. So if we look at where the marks are allocated, we get a mark for rearranging the equation, a mark for our value for distance of 1.54, and we then get a mark for our answer of 9.61 times 10 to the minus 7. This question is to do with entropy, which relates to the second law of thermodynamics, where we are told that titanium chloride can be made from titanium oxide, as shown in the equation stated. We are then asked to use the equation and the data in table 3 to calculate the Gibbs free energy change for this reaction at 989 degrees Celsius, and to then give our answer to an appropriate number of significant figures, and to then use this answer to explain whether this reaction is feasible. So straight away with this question, I would convert 989 degrees Celsius into Kelvin, because our delta S's units are measured in joules per Kelvin per mole. And to do this, we need to know the link between the two units of degrees Celsius and Kelvin. And this is that at 0 degrees Celsius is equivalent to 273 Kelvin. So we know that we need to add 273 to our 989, and this will give us a value of 1262 Kelvin for the temperature. Now, if we write out the free energy equation, we get delta G, measured in joules per mole, equals delta H, also measured in joules per mole, minus T, measured in Kelvin, multiplied by delta S, which is measured in joules per Kelvin per mole, where we want to work out delta G, and we have T, and we also have delta H, which is given as a value of minus 60 kilojoules per mole. What we are going to do now is use the equation for entropy change, which is entropy change equals SP minus SR, where SP stands for the entropy data for products and SR stands for the entropy data for the reactants. So if we sum the product and reactants using the data from table 3, whilst also taking into account the molar ratios, we will get, in large brackets, 253 plus 2 multiplied by 198 minus, also in large brackets, 50.2 plus 2 times 5.7 plus 2 times 223. And this, when added, gives us a simplified version of 649 minus 507.6, and therefore 141.4 joules per Kelvin per mole. Now we need to convert our delta H into joules per mole, and we do this by multiplying by 1000. and this will give us a value of minus 60,000 joules per mole, which means that all of our values that need to be are in joules. So if we plug all of this into our equation, we will get minus 60,000 minus 1,262 multiplied by 141.4. And this eventually gives us a value to an appropriate number of significant figures of minus 238,000 joules per mole. And if we convert this back into kilojoules per mole, which is the units that are stated in the question, we will get minus 238 kilojoules per mole. Now, if we look at whether this is feasible, we know that our value is negative. So because our value for delta G is negative, we know that our reaction is thus feasible. So finally, we now need to look at where we've been given marks. So we get a mark for our delta S equation. We get a mark for our value of 141.4 joules per Kelvin per mole. We get another mark for the free energy equation, a further mark for putting our values into this equation, then getting an answer of minus 238 kilojoules per mole, and then the sixth mark for stating why this value is feasible. This next set of questions require a lot of fact recall and are about some period 3 elements and their oxides, where the first question asks us to write an equation for the reaction of phosphorus with an excess of oxygen. Now, we know that phosphorus oxide is produced as phosphorus is slowly being oxidized, and this exists as P4O10. We also know that phosphorus exists as P4 and oxygen exists as O2. So if you put this together, we should have P4 plus O2 goes to phosphorus oxide, which is P4O10, and if we balance this, all we need to do is put a 5 in front of the O2, and that gets us the mark. We are then asked to describe a test you could carry out in a test tube to distinguish between sodium oxide and the product of the reaction in part 1, that we now know is phosphorus oxide. Now, the key fact here is that metal oxides are basic and non-metal oxides are acidic. So if we add water and then measure the pH using a pH probe, sodium oxide should have a higher pH than P4O10, as metal oxides are basic. And we get marks for saying reacting with water, measuring the pH, and then stating the distinction between the two compounds. Now we are asked to state the type of crystal structure shown in silicon dioxide and in sulfur trioxide. If we go back to GCSE, we know that SiO2 structure is like diamond and thus must be macromolecular. And if we break down SO3, we have two nonmetals, which we know is covalent bonding, so the structure must just be molecular. After this, we are asked to explain why silicon dioxide has a higher melting point than sulfur trioxide for 4 marks. And this question tests our understanding of bonding, but also tests our understanding of intermolecular forces. Now, between the atoms for SiO2, there is covalent bonding, compared to SO3, which has van der Waals forces between molecules. And we know that covalent bonds are stronger and require more energy to overcome than the van der Waals forces. So if you look at where we get the marks, we get a mark for stating covalent bonds, we get a mark for the van der Waals forces, a mark for knowing that covalent bonds are stronger than the van der Waals forces and thus require more energy. And that gets us 4 marks. For the next part, we are asked to write an equation for the reaction of sulfur trioxide with potassium hydroxide solution. So KOH is a base and SO3 is acidic as it is a non-metal oxide. And we know that when an acid and a base react, they produce a salt and water. The metal is always involved in the salt, so we are definitely going to have potassium in the name of the salt. And as we are reacting KOH with sulfur trioxide, we will form potassium sulfate, which has the chemical formula K2SO4, where two 1+ charges are needed to balance out the 1,2- charge on the SO4. If we now balance the equation, we can see that there is an imbalance for potassium straight away, so we can solve this by placing a 2 in front of the KOH, and this fully balances the equation and gets us the mark. This next question is very similar to the last and asks us to write an equation for the reaction of an excess of magnesium oxide with phosphoric acid. We know that metal oxides are basic, and we are given phosphoric acid, which we know is the acid. So again, we have an acid plus base reaction, where an acid plus a base gives us salt and water. Magnesium is the metal in this reaction, and will therefore be in the name of the salt. And as the acid is phosphoric, we will get a phosphate produced. Mg forms 2+ ions, and from H3PO4 we can decipher that the PO4 ion is in fact a 3- ion due to needing 3 1+ hydrogen ions to balance this out. So what we end up with is Mg3 PO42 plus H2O, where 3 Mg2+ ions are needed for the 2 PO4 3- ions, resulting in a compound with no overall charge. And if we look to balance the equation, we can see that we can balance the magnesiums by placing a 3 in front of our MgO. We can also see that we can balance our hydrogens by placing a 2 in front of our H3PO4 and then a 3 in front of our H2O. And this balances the equation and gives us the mark. For the final part of our question, we are asked to draw the displayed formula for the undissociated acid formed when sulfur dioxide reacts with water. Now, when sulfur dioxide reacts with water, we get H2SO3, and initially this may create an issue. But using our knowledge from organic chemistry, we know how to draw H2SO4, which looks like this, where the sulfur is bonded to 2 OHs and 2 double bonded oxygens. As H2SO3 is diprotic due to the 2 H's, we are definitely going to have 2 OH groups, meaning we will get this for our structure, where the central sulfur is attached to 2 OHs and 1 double bonded oxygen. And this gets us the mark.
For this question, we are told that solution A contains the following compound. We can see that this compound is going to be an example of a transition metal complex. And for this question, we need to state the type of bonding between the oxygen and the hydrogen in this compound. So we're looking at the water part of this compound, and if we've got a water molecule shown here, this is going to be bonded via a coordinate bond to the copper ion for this transition metal complex. Therefore, the type of bonding between the oxygen and the hydrogen in this compound is going to be covalent. For this part of the question, we need to state why the chloride ions within the compound are not considered to be ligands. So just to refresh, our compound has got the following formula here. So we've got a transition metal complex, and then we've also got our chloride ions. So the definition of a ligand is an atom, a group of atoms, or an ion which is coordinately bonded to a metal ion. Now, if we have a look at our complex here, the transition metal complex is the part within this square brackets, and that would actually have a formula of a 2 plus, because this is then going to be ionically bonded with the 2 chloride ions. There'll be 2 negative charged ions to balance out the 2 plus ion there. So therefore, the reason why they're not considered to be ligands is because the chloride ions are not forming a coordinate bond with the copper 2 plus ion. So it doesn't donate a pair of electrons there as well. So a coordinate bond is similar to a dative covalent bond. We just refer to it in the context of a transition metal complex typically. And that's where one atom or ion donates both of the electron pairs required for that bond there. So our chloride ion does not donate a pair of electrons. An excess of ammonia is added to a sample of our solution A to form a solution B. And for this question, we need to write an ionic equation for the reaction that occurs when solution A is converted into solution B, and we need to state the colour of solution B. So recalling that our solution A was that transition metal complex, if we're forming a solution B upon addition of excess of ammonia, this is going to be an example of a ligand substitution reaction. Specifically, we're going to be substituting out our ligands with some ammonia to form a new solution. So for our equation, let's start by writing out the complex which we started off with. So our solution A was this formula here. And the key thing is we need to write down an ionic equation. So solution A had the chloride ions ionically bonded there, but these are not actually taking place in our reaction because they're not a ligand, so they're not going to be substituting in or out. Therefore, they're just going to be spectator ions, so we don't need to include them there for this equation. So they're just spectator ions, so don't need to be included in our ionic equation. And we're adding our ammonia. And this is one of the ligand substitution reactions which you need to be able to learn and recall for this question. So for this particular reaction, we substitute out 4 of the water molecules for 4 ammonias. So we need 4 ammonias, and then the formula of our new transition metal complex, we've still got our copper 2 plus, and then we've got 4 ammonias, and then we've still got 2 waters as well in our complex. And that ammonia is neutral, the water is neutral, so we've still got a 2 plus charge. But then because we substituted out 4 of the waters for 4 ammonias, we've then got 4 waters left over there. And the colour of our new solution is another colour which you need to be able to recall and learn, and that's going to be a deep blue or a dark blue solution there. And for this question, it was 2 marks, so it was 1 mark for this ionic equation and 1 mark for the colour there. Aqueous sodium carbonate was added to another sample of our solution A to form a blue-green solid C. And for this question, we need to identify this solid here. So what we know is that we're going from our solution A, from our transition metal complex, and we're forming a solid. Therefore, this is going to be an example of a precipitation reaction, where we're forming a solid precipitate from two solutions. And the solid precipitate that we're going to be forming is going to be our solid copper carbonate. So it's a blue-green colour, and that's coming from the copper, from that transition metal. And it's going to be the carbonate there, which has come from the sodium carbonate. Reagent D was added to another sample of solution A, with the transition metal complex formula shown below, to form a yellow-green solution. We need to identify reagent D, which was added, and to write an ionic equation for that reaction which occurs when we form this yellow-green solution from solution A. So if we're going from a transition metal complex solution to a new solution, we've got another ligand substitution reaction going on here. And specifically, one of the complexes which you have to learn, which has a yellow-green colour for the solution, which is a copper-based complex, is the copper tetrachloride complex, which has got a tetrahedral structure. So this is one of the complexes you have to be able to learn, and with the colour as well. And to form this, we need a source of chloride ions, and our reagent D is therefore going to be our hydrochloric acid there. So for our ionic equation, we can include the whole of the HCl, or we can just use the chloride ions, because those are the ions which are actually taking place in this reaction here, whereas the H pluses are acting as spectator ions. So our equation, we've got our copper complex, and recalling again that I'm only writing out the transition metal complex from this, the charged part. I'm not including the chloride ions from solution A because they're acting as spectator ions, and we need to write an ionic equation rather than just an overall reaction equation. And we're reacting these with our chloride ions from that HCl, from our reagent D, and we're producing our copper tetrachloride complex. So therefore we're going to need 4 equivalents of the HCl, so 4 equivalents of those chloride ions, and we're substituting out the 6 waters. So we produce those on the right hand side of our equation. And just a quick check as well that our charges are balanced, so we've got 2 minus for our charge on the left hand side and 2 minus for our charge on the right hand side. So we've got a correctly balanced equation. And for this question, it's 2 marks, so it's 1 mark for the identity of reagent D, and then it's 1 mark for our ionic equation there. For this part of the question, we need to explain why colorimetry cannot be used in order to determine the concentration of the solutions containing this ion here. And in our answer, we need to refer to the electronic configuration of the metal ion. So for this question, with this copper complex, because we've got a negative charge overall, and we know that our chloride ions have got a 1 minus charge, if we've got 2 1 minus charges and a negative charge overall, that must mean that we've got a copper 1 plus ion in this complex. So let's start by thinking about what the electron configuration of that ion can be, and this will then lead us towards the rest of the answer. So in your periodic table, you'll be able to see that the atomic number of copper is 29. So therefore the electronic configuration is going to be as follows. So we're just building our way up through the different electronic orbitals. And the key thing is that once we get to our 4s and our 3d orbitals, instead of being 4s2, 3d9, copper has got the configuration of 4s1 and 3d10. And the reason why is because having this full d orbital with all of the electrons paired up gives the copper some extra stability there, which it doesn't have before. So then if we want the copper 1 plus ion, we can then lose that electron from the 4s orbital. So therefore we end up with a 3d10, so a fully filled d orbital for our copper 1 plus ion. And this is the key for this question. So we've got a full d orbital, where we've got 3d10 for the copper 1 plus. And this means that it's got stability. And therefore as well, because we've now got a full d orbital, we've not got a true transition metal at this point. Because we've got that full d orbital, so we're not going to get some of those classic properties, such as those coloured compounds, which we get with incomplete d orbitals. Therefore, we've got a colourless solution for this complex. And what this means is that it's not going to show up on colorimetry. So colorimetry involves the absorption of visible light. We can match the absorptions to certain concentrations of coloured solutions if we run a control graph. But if we've got a colourless solution, that means it can't absorb visible light. Therefore, it's not appropriate to use for colorimetry. And this is a 2-mark question. So there's 1 mark for mentioning the electronic configuration of that copper 1 plus ion. And then there's 1 mark for therefore making that deduction that it will be a colourless solution which can't absorb visible light or frequencies of visible light.
Describe how a student could distinguish between aqueous solutions of potassium nitrate, KNO3, and potassium sulfate, K2SO4, using one simple test tube reaction. Now, we know, by using our knowledge of testing for sulfate ions in this question, that using acidified BaCl2, which is barium chloride, will result in no visible change for KNO3, but there will be a white precipitate produced of BaSO4. And for extra information, there is actually an ionic equation that looks like this, which is Ba2 plus in the aqueous state plus SO42 minus in the aqueous state. That goes to BaSO4 in the solid state. And that gets us the 3 marks. Moving on to the second part of the question, we are asked to describe how a student could distinguish between aqueous solutions of magnesium chloride, MgCl2, and aluminium chloride, AlCl3, using one simple test tube reaction. So we know that we cannot use the test for chloride ions, as they are both present in these compounds. Now what we do know is that from fact recall, we will want to carry out a test using excess NaOH. So we know that MgCl2 is very insoluble, so we'll produce a white precipitate that will not redissolve with excess NaOH. This is then compared to AlCl3, which initially, when reacted with some NaOH, produces a white precipitate of Al, H2O3, OH3, and then when reacted with excess NaOH, gives the colourless solution Al, H2O2, OH4 minus. And this gets us 3 marks. This question tells us that there are several stages in the industrial production of methanol, with the first stage involving a gaseous equilibrium between the reactants methane and steam and some gaseous products, where figures 1 and 2 show the percentage conversion of methane into the gaseous product under different conditions at equilibrium. We are then asked to deduce the optimum conditions for the industrial conversion of methane and steam into the gaseous product, and to explain our deductions for 6 marks. The key with this question really is saying what we see. So if we start with figure 1, we have a relationship between temperature and the percentage conversion of methane at constant pressure. If we analyse closely, we can see that a temperature between 800 and 880 degrees Celsius maximises the yield, where after 900 degrees Celsius, the yield no longer increases. But we know that a high temperature requires lots of energy and is expensive. So here is a compromise. If we now look at figure 2, we can see that the same relationship, but with pressure rather than temperature, is also shown, where the yield decreases as pressure increases, and the lowest pressure gives the highest yield. But a low pressure may have a slow rate of reaction, so again a compromise may be needed between pressure and temperature. So we can deduce that the temperature should be around 880 degrees Celsius and the pressure should be around 1000 to 2000 kPa. Now this question is actually marked in stages, so there isn't necessarily an exact word that gets a mark, but as long as we talk about the deductions from figure 1 and figure 2, talk about the optimum temperature and pressure reasons and then explain them, we should get 6 marks. The next part tells us that the equation shows the final stage in the production of methanol, where 20.1 mole of carbon monoxide and 24.2 mole of hydrogen were placed in a sealed container. An equilibrium was established at 600 Kelvin, with the equilibrium mixture containing 2.16 mole of methanol. We are then asked to calculate the amount in moles of carbon monoxide and of hydrogen in the equilibrium mixture. Now, Kc is to do with concentrations, and for these types of questions, I would always use the ICE method, which relates to the amount of moles initially and at the end in the equilibrium, with the change in the middle. So if we draw out the table and insert our values, we have ICE vertically with CO, 2H2 and CH3OH horizontally. We then have 20.1 and 24.2 in the initial, and then 2.16 in the equilibrium mixture. So we know that there must have been 2.16 moles in the change, as our initial value for this is 0. And if we use the molar ratios, we know that there are 2.16 and 2 times 2.16 in the change for the reactants, not forgetting the minus sign now, as CO and H2 have reacted to form CH3OH. So we can now calculate the total amount of moles in the equilibrium mixture using subtraction, where to 3 significant figures we will get 17.9 and 19.9, and this gets us both marks. Moving on to the final part, we are then told that a different mixture of carbon monoxide and hydrogen was allowed to reach equilibrium at 600 Kelvin. At equilibrium, the mixture contained 2.76 mole of carbon monoxide, 4.51 mole of hydrogen, and 0.36 mole of methanol, with the total pressure being 630 kPa. We are then asked to calculate a value for the equilibrium constant, Kp, for this reaction at 600 Kelvin and state its units for 6 marks. Now, Kp is very similar to Kc, but rather than concentrations, it is to do with partial pressure. So the first step with big Kp questions is to always add up the amount of moles given in the equilibrium mixture, and when we sum these values, we get 7.63. Now, this allows us to get the mole fraction, which is calculated via the number of moles of gas divided by the total number of moles of gas. So now doing 2.76 divided by 7.63, 4.51 divided by 7.63, and 0.36 divided by 7.63, we will get values of 0.3617, 0.59108, and 0.04718. We can check that this is correct, as our mole fraction should add up to 1, and if we store these values as their absolute value, we will get a value of 1, which means that they are the correct values for the mole fraction. So now we need to work out partial pressure, which is calculated via the mole fraction multiplied by the total pressure. And when we multiply our 3 mole fraction values by 630, which is our value for total pressure, we will get to 3 significant figures: 228, 372, and 29.7. Now we have all the information we need, so when we put this into our equation to work out Kp, where the partial pressure of the product is divided by the reactants, not forgetting the molar ratios, we will get the partial pressure of CH3OH divided by the partial pressure of CO multiplied by the partial pressure of H2 squared. So if we put in our values now, we will get 29.7 divided by 228 multiplied by 372 squared, which gives us an answer of 9.413 times 10 to the minus 7. Now for the final mark, we need units. Now we have 1 mole on the top and 3 moles on the bottom. So we have 1 divided by kPa squared if we cancel out a kPa on the top and a kPa on the bottom. And when we flip an indice, we get a negative power, so what we are left with is kPa to the minus 2. So the marks are allocated here for the value of 7.63. We get 2 marks for getting our partial pressure values. We then get a mark for writing out the partial pressure equation. We get a mark for our units, and we also get a mark for our final answer. And this is the 6 marks. This question shows us table 4 that has some electrode half equations and their standard electrode potentials, where we are asked to deduce the oxidation state of nitrogen in NO3- and in NO for 1 mark each. So if we use our knowledge of oxidation numbers, we know that oxygen has an oxidation number of -2, as it has to gain 2 electrons to get a full outer shell. Now, if we do -2 times 3, we get -6, knowing that we need to get -1 for the overall compound. So we can set up an equation of -6 plus x equals -1, and if we rearrange for x, we will get an answer of +5. Now, if we do the same for NO, we can use the same fact that oxygen has an oxidation number of -2, where there are 2 electrons needed to be gained to get a full outer shell, and we know that the overall charge of this compound is 0, so we have -2 plus x equals 0, meaning nitrogen must have an oxidation number of +2. Moving on, we are then asked to state the weakest reducing agent in the table. Now, given the superlative weakest, we know that we will have to go for either the top or the bottom in the table. For this, we can use three key ideas. The first being what a reducing agent is, and this is an agent that reduces something and in itself is oxidized. The second being a bit of a cheat but a very useful tool to have, where the cell with the most positive EMF contains the weakest reducing agent. And then the third being the acronym oil rig, where oxidation is loss and reduction is the gain of electrons. So if we look at the cell with the most positive EMF, we can see that the options for the weakest reducing agent is either Cl2 or Cl-. Now in this equation, the Cl- is losing electrons, which using oil rig means it is being oxidized, and this matches with our definition of a reducing agent of being an agent that reduces something but is in itself oxidized. So our answer is Cl-. We are then asked to write out the conventional representation of the cell that has an EMF of plus 0.43 volts. So the first job is to find the two half equations that have a difference of 0.43 volts, and we can see that the two equations are the ones that involve copper and iron 3 plus ions. So if you write both out in full, we will have Fe3 plus E minus goes to Fe2 plus, and then Cu2 plus 2E minus goes to Cu. Now the half equation that has the most negative EMF goes backwards, and this is just so we do not have two half equations in the form of reduction, where the half equation going backwards shows oxidation. So now we can begin to write out our cell, where we start with the half equation that is most negative on the left. So we have Cu in the solid state and Cu2 plus in the aqueous state, with a phase boundary shown by a vertical line as there is a change in state. We then have a double dashed line as there is a salt bridge needed, and this just allows ions to move, and this is shown by a double vertical line. And then we have Fe3 plus in the aqueous state and Fe2 plus also in the aqueous state, but with a comma in between, and also a platinum electrode in the solid state, as there is no solid or change in state between the iron ions. And this gets us the 2 marks. For the final part of this question, we are asked to use data from table 4 to identify an acid that will oxidize copper, to then explain our choice of acid, and to use this data to suggest a possible equation for the reaction, and to calculate the EMF of the cell that has the same overall reaction. So given that we need to oxidize copper, what we need is an acid that has a more positive EMF value. As the more positive the EMF value is, the better oxidizing agent something is. The only possible solution is therefore nitric acid, which has the chemical formula HNO3, and this is the best option as the half equation with NO3- has a value of plus 0.96 compared to plus 0.34. And using the two equations, we can get another mark by working out the overall EMF value by doing 0.96 take away 0.34, which gives us an answer of 0.62 volts for the overall EMF. Now for the final mark, we need to write out an overall equation. So if you write out the two equations first, we will get NO3- plus 4H plus 3E- goes to NO plus 2H2O, and then Cu2 plus 2E- goes to Cu. So again, the half equation with the most negative EMF goes backwards, so we will get Cu goes to Cu2 plus 2E-, Then we will need to balance the electrons in the equations, so by multiplying the top equation by 2 and the bottom equation by 3. This then gets us 2NO3- plus 8H plus 6E- goes to 2NO plus 4H2O, and then we'll have 3Cu goes to 3Cu2 plus 6E-. Then what we need to do is to take all on the left-hand side of the equations and combine, and then take all on the right-hand side of the equations and combine. And doing this, we should get 2NO3- plus 8H plus 6E- plus 3Cu goes to 3Cu2 plus 6E- plus 2NO plus 4H2O. Now we can also cancel out the electrons, and we can then be left with 2NO3- plus 8H plus 3Cu goes to 3Cu2 plus 2NO plus 4H2O. So if we look at where the marks are allocated for this question, our first mark is for stating that we need to use nitric acid. Our second mark is for stating that our cell with an EMF of 0.96 is greater than 0.34. Our third mark is for getting an answer for our EMF of 0.62. And then our final mark is for working out the overall equation. And this gets us all 4 marks for this question.
This question is about compounds containing ethane dioate ions. We're told that a white solid is a mixture of sodium ethane dioate, ethane dioic acid dihydrate, and an inert solid. And a volumetric flask contains 1.9 grams of the solid mixture in 250 centimeters cubed of an aqueous solution. We're then told that 2 different titrations are carried out using the solution. In our first titration, 25 centimeters cubed of the solution was added to an excess of sulfuric acid in conical flask. The flask and contents were then heated to 60 degrees and then titrated with a 0.02 mole per decimeter cubed solution of potassium manganate 7. When 26.5 centimeters cubed of potassium manganate had been added to the solution, it changed colour. And the equation for this reaction is shown below. So what we've got here is going to be a redox reaction, where our potassium manganate is reacting with all of our ethane dioate ions there. So we've got some of these ions from the sodium ethane dioate and from the ethane dioic acid dihydrate there. So let's have a think about the second titration now. So in our second titration, 25 centimeters cubed of the solution again was titrated with a 0.1 mole per decimeter cubed solution of sodium hydroxide, and we're using phenolphthalein as an indicator. Our indicator changed colour after the addition of 10.45 centimeters cubed of that sodium hydroxide solution, with our equation here shown below. And this equation is going to be an acid-base reaction, because our sodium hydroxide is only going to react with the ethane dioic acid part from our white solid, so it won't react with the salt from the solid. So we need to use all of this information to calculate the percentage by mass of sodium ethane dioate in that white solid, making sure that we give our answer to an appropriate number of significant figures and showing all of our working. So what we can do is we've got 2 different titrations. So let's start by working out some moles from each of these. So I'm just going to call these titrations 1 and 2 very clearly. So with titration 1, we've been given our concentration and volume of potassium manganate. So we can use this to work out the moles of potassium manganate. We can use this by doing our moles equals volume times by concentration equation. And the key thing is that we need to convert our volume into decimeters cubed so that they match up with the moles per decimeter cubed units for the concentration. Therefore, we've got 26.50 divided by 1,000, multiplying that by that concentration of 0.0200, and in the calculator that will give you a value of 5.3 times 10 to the minus 4 moles. So now we've got our reaction equation here, and we can see that our mole ratio of the manganate to our ethane dioate ions is going to be a 2 to 5 ratio. Therefore, to work out the moles of the ethane dioate ions, what we can do is we can divide our answer by 2 to work out the value of 1 mole, and then we can times that by 5. And this gives a value of 1.325 times 10 to the minus 3 moles. And this is going to be the moles of the ethane dioate ions in the 25 centimetre cubed sample, because we use the 25 centimetre cubed sample of our solution in this titration. And because we've got the ethane dioate ions, the key thing here is that this has come from the ethane dioic acid and from the sodium ethane dioate as well. So we'll just make a note of that here. So that's from the acid and from the salt. So now let's have a look at titration 2. So we've been given a volume of our sodium hydroxide solution added, and we've got our concentration of sodium hydroxide. Therefore, we can now work out the moles of our sodium hydroxide. So I'm just going to write down the hydroxide to simplify, think about the ions involved. So the moles of our hydroxide ions, again converting our volume to decimeters cubed by dividing that by 1,000. So going from centimeters cubed to decimeters cubed, we're dividing by 1,000. Our working out for this one is going to be 10.45 divided by 1,000 multiplied by that concentration, which is 0.1. And this gives a value of 1.045 times 10 to the minus 3 moles. Again, let's look at the mole ratio now in our equation to work out what our moles of our ethane dioic acid will be. So we can see that we've got a 1 to 2 molar ratio. So therefore, to work out the moles of our ethane dioic acid, we've got to divide our answer by 2. So the moles, therefore, of our ethane dioic acid is going to be our answer divided by 2, which equals 5.225 times 10 to the minus 4 moles. And again, this is in our 25 centimetre cubed sample, because that's the amount of our solution which we used in this titration. And let's just make a note here as well. This is only going to be from our reaction with the acid, because that sodium hydroxide will not react with the salt. It will only react with that acid, with that proton donor there, the ethane dioic acid. So now we've worked out the moles of our ethane dioate ions from the sodium ethane dioate and the ethane dioic acid. And then in the second titration, we worked out the moles of just our ethane dioic acid. So what we can do now is we can subtract those to work out the moles of just the sodium ethane dioate within that 25 centimeters cubed. So the moles of our sodium ethane dioate in 25 centimetres cubed is going to be our 1.325 times 10 to the minus 3, subtract 5.225 times 10 to the minus 4. We can put that in brackets as well to make it a bit easier in the calculator. And that gives us a value of 8.025 times 10 to the minus 4 moles. And that's in 25 centimetres cubed. But originally we made our solution to 250 centimetres cubed. So now we need to work backwards to work out what our moles would be in 250 centimetres cubed. Therefore, we're going to have 10 times the amount of our moles in 250 centimetres cubed. So the moles now of our sodium ethane dioate in 250 centimetres cubed is just going to be that times by 10. So it's going to be 8.025 times 10 to the minus 3 moles now. So now it's all coming together at the end. We've got the moles of our sodium ethane dioate, which we have in our 250 centimetres cubed. We've got the mass of our solid mixture here. So we can use this mass in a minute, but what we can do now is we can work out the mass of our sodium ethane dioate, which corresponds to the number of moles that we've got. So we can do this by multiplying our moles by the molecular mass of that sodium ethane dioate. So our mass of the sodium ethane dioate in our sample is going to be equal to the moles times by the molecular mass. So the molecular mass is going to be equal to 2 lots of 23 plus 2 lots of 12 for our carbon plus 4 lots of 16 from our oxygen, and that gives us a value of 134. So to work out the mass of our sodium ethane dioate then, we're going to do our 8.025 times 10 to the minus 3 moles times by 134, and that equals 1.0735 grams. So now we've got our mass of sodium ethane dioate. We know the mass of our solid mixture which we dissolved, that was 1.90 grams. So to do a percentage by mass, we just need to divide our mass of sodium ethane dioate by our original mass and times that by 100. So now our percentage is going to be 1.035 divided by 1.90 times by 100, and that's going to equal 56.6%, and that's to 3 significant figures, because we've got to give our answer to an appropriate number of significant figures here. And if we look at our data, this has all been given to a minimum of 3 significant figures. Therefore, our answer needs to be given to that minimum significant figures, which the data is being given to, which is 3. So that's why we leave it as 56.6. So there were 8 marks for this question, and let's see where those marks have come from. So our first mark was for working out the moles of our manganate ions, and then the second mark was then equating that to the moles of the ethane dioate ions by dividing by 2 and multiplying by 5, and that was in our 25 centimetre cube sample. The next mark was for somewhere working out the moles of those hydroxide ions. So even if we weren't sure of where to go any further, 2 marks were for working out the initial moles from that data given for each of those titrations. The next mark was then for equating our moles of hydroxide ions, doing our mole ratios to work out the moles of that ethane dioic acid. So that's half the marks just for working out moles and using mole ratios there. So now let's move on to the second half of the marks. So there's a mark in there for subtracting those 2 moles from each other to get the moles of that sodium ethane diorate in 25 centimetres cubed. Now the next mark is then for remembering that we've worked out the moles in 25 centimetre cubed, so then multiplying our answer by 10 to get the moles in 250 centimetres cubed. So the last two marks were firstly for working out the mass of the sodium ethane diorate by multiplying the moles by its molecular mass of 134. And then that final mark is for getting our answer for that percentage by mass of 56.6, and it has to be to 3 significant figures to get that final mark there. And that's how you answer this question. Ethane diorate ions react with aqueous ion 3 ions in a ligand substitution reaction. And for this question, we need to write an equation for this reaction and suggest why the value of the enthalpy change for this reaction is close to 0. So I'm just going to draw out the ethane diorate ions to one side here. So we know that they have a formula of C2O4 2-. What does this actually look like? Well, we've got 2 carbon atoms, like so. They're bonded back to back with carbonyl bonds, and then we've got single bonded oxygen, and they've each got a negative ion on there. So our aqueous ion 3 ions, if we need to draw this for a ligand substitution reaction, that complex there is going to be where we've got our ion, and that's going to be in a hexa-aqua complex for the aqueous, and we show it this way so that we can show the full ligand substitution. And if we get the ligand substitution, we're going to be substituting these waters out for 3 of our ethane diorate ions. And that's because these ethane diorate ions are bidentate, which means that they can form 2 coordinate bonds per molecule. Therefore, our reaction equation is going to look like so. So we've got our hexa-aqua ion 3 plus complex. We're reacting it with 3 lots of the ethane diorate ions, and these are going to substitute out the water. We're still forming 6 coordinate bonds, but we have a bidentate ligand, so we only need 3 of the ethane diorate ions. But now the charge is going to be slightly different for the complex because the ion is in 3 plus oxidation state, but we've got 3 lots of our -2 charged ions. Therefore, we've got 3 plus and then we've got 6 minus. So that gives an overall charge of 3 minus. And then we've got our 6 waters, which we substituted out. And checking the charge, we need to have the same charge both sides. So we've got 3 minus on the left and 3 minus on the right as well. So then thinking now about why the value for this enthalpy change of this reaction is close to 0. The enthalpy change of reaction, we can think about this in terms of bonds being broken and bonds being made. And if it's close to 0, then that means that the energy required to break the bonds on the left-hand side will need to be very similar to the energy produced when we make the bonds on the right-hand side. And if we look at our bidentate ligand here, these oxygens are the ones with the lone pairs. So these are the ones which are going to form the coordinate bonds with the central ion. And in our hexa-aqua complex, again, it was the water with the lone pair on the oxygen. Therefore, it's the oxygen forming that coordinate bond to the ion. So we've got iron-oxygen coordinate bonds in both of these complexes. So therefore, the reason why the value of the enthalpy change of reaction is close to 0 is because we've got the same number and the same type of bond being broken and made. So that's key as well to have the same number. So we're breaking 6 coordinate bonds on the left and we're making 6 coordinate bonds on the right. So it's 6 iron oxygen bonds in question here. So then it was 2 marks for this question. So the first mark was for that equation for the reaction, and then the second mark was for saying something along these lines as to why we've got an enthalpy change close to 0. For this question, we need to draw the displayed formula of the iron complex which was produced in the reaction above. So just to note, that complex had the following formula. So it was iron, and then we had 6 coordinate bonds because we had 3 units of our ethane dioate bidentate ligands there, and that had a 3- charge on it overall. We also need to indicate the value of our oxygen-iron-oxygen bond angle, and we need to state the type of isomerism which is shown by this iron complex. So let's start by drawing out the complex and displayed formula. So we've got our central iron metal, and then we've got an octahedral complex here because we've got 6 coordinate bonds. So I'm just going to start by drawing those bonds out in the 3D shape. So we have 2 in the plane, we have 2 wedged, so they're coming out towards us, and 2 dashed because they're going behind us. And each of these bonds is to an oxygen. So I'm just showing that lone pair just to make that coordinate bond really clear. And then we've got 3 ethane dioate bidentate ligands in total. So these oxygens are bonded to their carbons, and then we've got that carbonyl bond on either side. So then we just repeat this going around the molecule. Finishing it off in that way. And the last thing to do is to just draw on some brackets and then put the overall charge outside the brackets. We do it in this way just because it's a bit easier and less messy than writing the charges on each of the different atoms involved, because otherwise the whole diagram could get quite messy. So because this is an octahedral complex, our oxygen, iron, oxygen is going to have a 90-degree bond angle. And also, because we've got this octahedral complex with these bidentate ligands, we're going to have optical isomerism there. So that's where we've got a pair of enantiomers which reflect plane polarized light in opposite directions. And it's all to do with which position these ligands are bonded to. So in this diagram I've bonded them in this way with the gaps left where they are. But alternatively, you could have the ligands bonded here, here, and here, and that will give you the other optical isomer, so a different 3D spatial arrangement of atoms. So this question was 3 marks. So there was 1 mark for drawing out our displayed formula of the complex, 1 mark for the bond angle there of 90 degrees. They would also accept 180 degrees if you chose to go across this combination of oxygen, iron, oxygen, for example. And then the final mark was for naming the optical isomerism. Ethane dioate ions are poisonous because they react with iron ions in the body. And then we are told that ethane dioate ions are present in foods such as broccoli and spinach. And for this question, we need to suggest one reason why people who eat these foods do not suffer from poisoning. Well, one sensible conclusion to make would just be that the ethane dioic acid present is only going to be in very small quantities or a very low concentration in these foods. So let's write that down as our answer. So the ethane dioate ions are only present in low concentrations or small quantities. And we only need to give the one reason here to get that mark. If you gave multiple reasons and one of your reasons was incorrect, then you might not get that mark there. So it's important to just give the one reason instead of listing several reasons. And this will also make sure that we're saving time when we're answering the questions.